Okay, so these are the two Kepler's law problems that are at the end of that lecture. And so let's go through and do these two examples. So the first example, so we went ahead and we've just written Kepler's third law up here. And let's start with part A. Okay, now part A says, suppose you double the Earth's distance from the Sun. How would that affect the Earth's orbital period then? Okay, so we basically don't need to use the full mathematical glory here of Kepler's third law. We can basically use kind of an argument, a very simple argument, since we're just doubling the radius. Everything else here is staying the same. The mass of the Earth is the same, or sorry, the mass of the Sun is the same. G doesn't change. And all that's changing is this. So we know what the period is for Earth's current distance, so we can just see what happens when we double r. Okay? So if we double the radius, okay, we're doubling that guy. Well, you have to cube it. So if you're doubling the radius, you've got to cube the radius. So that means the right side of this equation is now going to be 8 times larger. Okay? Since 2 cubed is 8. So t squared, this whole thing is now 8 times larger than when the radius gets 2 times larger. So to figure out how that affects t, well, t squared gets 8 times larger. So t gets square root of 8 times larger, because the square root of 8 is the square root of 8. So therefore, if we've doubled the distance of the Earth from the Sun, the orbital period would get square root of 8 times larger than it currently is. So that means the orbital period would be, since it's 1 year, as we know it today, it would now be square root of 8 years. Okay, which is 2.83 years. Okay. Now, the second problem, we'll just call that part B. I didn't label it as part B in the lecture. It tells us to calculate the orbital distance of a geosynchronous orbit. In other words, an orbit such that the satellite stays exactly above the same point on the Earth at all times. Okay, if that's the case, the orbital period of that satellite around the Earth would be 24 hours, because that's how long it takes that exact same spot on the Earth to go around once, 24 hours. So for that satellite to stay above the same part of the Earth, its orbital period is 24 hours. Okay, so that's the geosynchronous orbit, or as the text calls it, a geostationary satellite. Okay, now to use Kepler's third law, we need this in seconds. So 24 hours, once you convert it to seconds, you got to multiply it by 3,600 seconds in an hour. You get 86,400 seconds. Okay, so now we can plug it into Kepler's third law. So the period is 8640 seconds, 86,400 that is, squared. That equals 4 pi squared divided by g, which is, again, 6.67 times 10 to the minus 11. The mass of the Earth is 5.98 times 10 to the 24 kilograms. And then we have r cubed over here. So at this stage, it's just an algebra problem. You take this squared, divide it by 4, divide it by pi squared, times this, times that, and you have r cubed. You then take the cube root of all that, and you find that the radius of this geostationary orbit is a pretty big radius, pretty big distance. It's 4.23 times 10 to the 7 meters. Okay? The radius of the Earth is only about 6 times 10 to the 6 meters. So this is about 6 or 7 times, roughly, the radius of the Earth. So a geostationary orbit is pretty far away from the Earth then. Anything that's closer to the Earth than this takes longer to go around the Earth. I'm sorry, it goes around faster. It has to be moving faster because the force of gravity is stronger. So satellites closer than this distance will go around faster than 24 hours. Orbits for satellites that are farther away than this take longer than 24 hours. So at just this distance then, 6 or 7 times the Earth's radius, that satellite would hover exactly above the surface of the Earth at all times.